Hi everyone. My name is Boyan. I'm one of the founders and the CTO of StorPool Storage, who are one of the sponsors of this event and kind of popular in the CloudStack ecosystem. We do a bunch of stuff around CloudStack. We've had a few presentations this time. This one is specifically about HCI infrastructure, and this is my agenda. So I'll go through the standard quote-unquote way of how people build clouds, and then introduce this concept of hyperconverged infrastructure. A lot of you are familiar with it, but we have a little bit of a different spin on it, or do more. We have this marketing term we call beyond HCI, which I'll explain. And I'll talk about how we do the control plane, the secondary storage, the backups in this HCI solution. And I'll show some numbers of how fairly compact HCI deployment, what it could do for you in terms of capacity for virtual machines. So a cloud is four things: compute, networking, storage, and a cloud orchestration system like CloudStack that manages all of these resources, implements various services that you provide to your internal customers, external customers. Typically, for example, if you look at the documentation of CloudStack, the way to build a highly available control plane includes 2 load balancers, 3 management servers, and 2 databases. Traditionally, the way people have built highly available storage systems is a couple of fiber channel switches, storage controllers, storage shelves. They would have secondary storage on an NFS server, and they would have a separate physical servers for their backup solution. You have virtual machine networking, management and out-of-band networking, and then the meat of the whole thing, the place where virtual machines run, which is compute hosts. And this is a lot of components, right? So for someone, especially if, well, in most cases, these are just too many components for what you're trying to, what you're getting back, right? So how can we do better? The way, like the most obvious one, traditionally when, a lot of times when people talk about, they put us in this software-defined storage box, and they say, what you guys do and what other software-defined storage solutions do is you replace the storage box and you get rid of the fiber channel box and just replace that with a bunch of storage nodes. It's not a scale-up architecture, it's a scale-out architecture, and that's the box we put you in. Doing it this way just misses a lot of opportunity for optimization. So HCI works like this. You have your compute hosts, your storage nodes, with a scale-out storage solution like StorPool. StorPool specifically has a client, a driver in the compute hosts. And then you merge the two, you run your storage cluster across the compute nodes, and the client is still there. So there is no kind of redundancy of data in the storage system is across storage nodes. There is no kind of, you don't lose redundancy, for example, right? You don't lose performance because you've folded the storage and the compute on the same hosts. So redundancy across storage nodes, parallel, in our case, a very parallel storage system. So each volume is spread across 100 NVMe drives underneath. So far, like merging compute servers with storage nodes, when people say HCI, this is usually what they mean. In our case, primary storage runs on the compute nodes. You don't need a special network. It's just an Ethernet network. You can use the same switches that you use for your virtual machines. There are no dedicated storage boxes. And the hardware resources for your primary storage system are just a bunch of NVMe drives, a few CPU cores, a little bit of memory out of each compute node. Our stuff, is extremely efficient. So you get a lot of performance from very modest hardware configuration. Like you don't need, I don't know, you don't need hundreds of NVMe drives to get millions of IOPS, right? It's a very modest hardware configuration. Beyond this, basic HCI, first, our HCI solutions, they have all the capabilities of a standalone storage system. So for example, if you have a VMware deployment, you can do start with an HCI cluster and expose iSCSI from it to your VMware deployment. If you have other use cases around, you can add just compute nodes, etc. You can run the CloudStack control plane on the compute hosts. You can run secondary storage on the compute hosts, and you can do backup services, on-site backup services on the compute hosts as well, right? So if we start again by, these are the components you need to build the cloud. We're taking them one by one, control plane, put it in the compute hosts, secondary storage, put it in the compute hosts, on-site backup services, also in the compute hosts. HCI node. How do we do secondary storage? We have an NFS highly available virtual machine, which is the image for that, the configuration for that is part of what we do. And the high availability mechanism of that is also part of what we do. So this is not a VM managed by CloudStack. It's a VM, the StorPool cluster takes care of it being available, bringing it up when a node falls down, moving it to another host if you're doing maintenance on one host, etc. So I'll explain that a little bit more. Do the same thing with the CloudStack control plane. So instead of, I have a slide on that. Let's move on. I'll talk a little bit about the control plane later. So in order for this thing to work, there are several things. One is resource allocation and isolation. So it's built in such a way that like CPU usage, memory usage of your VMs does not impact the storage system. They're isolated on different CPU cores, and kind of providing this resource isolation and allocation is part of the HCI solution. Redundancy schemes for the NFS and CloudStack HAVMs, they're not active-passive. They're a single active VM, it's an HAVM. If a host dies, it's restarted somewhere. There is obviously some time it takes for the VM to be restarted, but it's considered short enough that it doesn't affect your overall availability numbers. For both of these, this time it takes to restart does not mean errors. It means, for example, the CloudStack UI is unavailable for a minute, or it means the NFS service is stalled, unavailable for a minute. It doesn't mean you see I/O errors or anything like that. The way we build large environments with this concept is you have multiple reasonably sized clusters. Each of these clusters is simple, provides the maximum availability inside, and we minimize the dependencies between clusters. So they're if you have 10 clusters, the availability you get out of each individual cluster is the same as if you had one cluster. Building a large environment doesn't increase your complexity. It's just the same building block repeated multiple times. But we still permit, enable migrating workloads or balancing your load between these separate HCI clusters. Promised I'll talk a little bit about the control plane. So instead of load balancers, 3 management servers, clustering between the management servers and a database, it's just an HA VM. You don't need any extra to keep the control plane virtual machine up. You don't need any cluster software or configuration. It's all part of what we provide. This is as a reference for other places where you can see something similar. In OpenStack, in some OpenStack deployments, they have this concept of under cloud, over cloud. So they build a small cloud, they deploy the CloudStack control plane in that under cloud, they call it. And then this OpenStack control plane controls their actual cloud. This is in a way like that, but it's a lot simpler. There is, in this solution, there is a clustering, a high availability mechanism, the ability to bring up a VM and the CloudStack VM, which is outside of CloudStack, and it needs to be outside of CloudStack because of the kind of a chicken and a egg problem. You can't have CloudStack manage the VM that runs CloudStack. So you have a relatively simple orchestration to run the secondary storage in the CloudStack VM, and then the CloudStack VM manages the rest of your virtual machines, networking, etc. The bigger and more complex is rarely provides better availability. So in the standard architecture, in order to make that highly available, there is a pair of load balancers and a cluster between them, 3 management servers, database, etc. Just adding these additional components decreases availability, generally speaking. And because of that, a simple solution like this might have better availability than the much more complex HA setup you would do with CloudStack, depending on a lot of factors that don't fit in a slide. StorPool on secondary storage, CloudStack requires basically a shared file system for secondary storage. The way we provide that is a virtual machine with NFS inside. StorPool takes care of the availability of that NFS share, which is used for secondary storage in CloudStack. And a lot of the actions, depending on what storage you have been using, a lot of the actions that in CloudStack would be when you create a snapshot, that means copying all of the VM's data to a QCOW file on secondary storage. With StorPool and with some other storages, this functionality remains, snapshots, etc., they remain in the primary storage system, which means that creating a snapshot, creating a volume from a snapshot, creating a VM from a template, they're all instantaneous operations. It's not you ask for it and then it takes time for it to copy the data over, which means it's a relatively small NFS footprint. There is very little things left in there, like ISO images or something. And by putting secondary storage as a VM on the HCI cluster, we eliminate the need of like external infrastructure to support your CloudStack deployment. And the last one is on-site backups. So the choice between in one location you would have a backup server and you would send copies of your snapshots or incremental snapshots from your primary environment to the backup server. The alternative to that is to use snapshots in the primary storage solution as on-site backups. I kind of need to warn you that this doesn't serve the same function as off-site backups. So If you have fire in your data center, this wouldn't protect you. So the offsite backups you still need to do. This is separate from that. But this gives you, for example, it gives you instantaneous restores for your users. Like when a user asks for a clone of yesterday's data in the virtual machine, they get that instantaneously. They don't need to wait for it to be copied from the backup server over, etc. Right? With us, there is essentially no overhead in for creating, deleting, keeping snapshots. Creating a snapshot is instantaneous. You don't pause the VM, or you don't need to wait for it to happen. It's just you say create me a snapshot, you get a snapshot. And the topic of offsite backups and disaster recovery is a separate topic. We have some great solutions for that as well, but it's not part of this presentation. In this one, we are talking about how to build the primary infrastructure in the most efficient way. So on to the numbers. So to turn that into like more concrete scenario, first you need to decide what your optimization goal is. For if you go towards maximum density, cramming as many VMs as possible in per rack unit, is a different, you get a different result, a different hardware configuration versus if you have some other optimization goals. For a lot of people, the optimization goal would be something like the lowest total cost of ownership per particular type of VM. It wouldn't be maximum density or the absolutely fastest possible single virtual machine. There are also valid optimization goals, just the one we've chosen here is lowest TCO per delivered resource. So in a 5-server HCI cluster, you get something like 6 terabytes of usable memory. We say we don't use 7.5 terabytes of memory because if one of these servers needs to be in maintenance, you need some additional space to put your VM somewhere. 96 cores per server, 4 times 8 terabyte NVMe drives. With StorPool, with our 2+2 erasure coding scheme, that gives you about 70 terabytes of usable space. The 2+2 scheme is has it can tolerate 2 faults, so 2 nodes could be down and you still have your data and access to it. It has relatively low power density, so it's about 300 watts or less per rack unit, which means it's easy to cool. This is often in designing deployments, designing data centers. This is often underestimated. The additional power you need, if you just doubled, say you doubled the power density, the additional power you need to push that amount of air through a single rack unit is significant. It could be like 100 watts just to push the air you need to cool 500 watts in a single rack unit. So the lower density also helps with overall efficiency of kind of the power demands. In this setup, you could run 1,450 VMs with this kind of size. Obviously, if your VMs are twice as big, you'll run half of them or something. If they're twice as small, you run twice as many. Additional info about the VMs. Redundancy of memory is n+1 in this calculation. There is no memory over subscription, so all the memory is kind of fully reserved, allocated. CPU over subscription is 3:1, so there are 6 vCPUs per core, which is 3 vCPUs per thread, but because of varying load and CPU usage of your VMs, it then usually ends up being your physical CPUs end up being not 100% loaded all the time. There is, we think 3-to-1 is reasonable. We've seen, depending on use case, some customers go to 5-to-1, some customers go to 1, like no CPU over subscription, but it just really depends on what your workload is, what your VMs need. And 2-to-1 storage over subscription. Storage over subscription is, we define as the ratio between provision size, so this 100 gigabyte disk, and data stored in the storage system. This 2-to-1 ratio comes, some of it comes from clone provisioning. A significant part of it comes from thin provisioning, and just the VM has a 100 gigabyte disk, but it does not necessarily have 100 gigabytes of data stored inside. And in a well-built KVM environment, you can use this remaining provision space to give to other users. And last note on the numbers, this setup has a very high hardware utilization. So all these additional services that we crammed into the compute nodes and renamed them to HCI nodes, and they only take a few % of the resources of the compute nodes. Depending on like various parameters you could tune, this could be 4%, could be 7%, you know, for everything, for primary storage, secondary storage, control plane, integrated backups, all of these services you fit into the HCI nodes. You eliminate all external dependencies, all external boxes and infrastructure that you have outside of the compute nodes. And your deployment ends up being much simpler, much more efficient. What can be done to improve efficiency even further? The kind of the one that's not on the list is you can build setups which are optimized for your workloads, for your profile of sizes of VMs and load and types of applications you run. Random example, within roughly the same price, you could do a single socket server or a dual socket server. There are differences between the two. A big difference is that a dual socket server would have more memory bandwidth. So if your application needs that, maybe you do that. So there's a lot to be gained by optimizing the setup for the way your VMs work, the way your VMs behave. An easy one is if your cluster is not 5 nodes, but it's 11 or more nodes, why 11? Ask me after the talk. You can use more efficient storage redundancy schemes. You can have less overhead for memory capacity redundancy. And the difference is on the storage redundancy schemes, it's significant. So it's between 2 data, 2 parity, which is 2 times overhead for just redundancy of the storage versus 8 data, 2 parity, which is 50% overhead for storage, for redundancy of the data. You could go to higher CPU over subscription, but it depends on your use case. So if you're selling very low utilization VPSs for $10 a month, you might go to much higher CPU over subscription. You could do higher storage over subscription, also depending on the use case. So if you have a lot of clone provisioning and your VMs are short-lived, you could do, like in StorPool at least, it's you could do 1,000 100 gigabyte VMs with 0 storage overhead. So you have your base images, you create 1,000 clones of this base image, that doesn't take any extra space. So if your VMs are short-lived and you have a lot of clone provisioning, you could increase your storage over subscription. You could look towards memory oversubscription with things like KSM is the memory deduplication technology in KVM in Linux, ballooning in the virtual machines, which kind of the downside of that is that's visible by your users, so that they see that they don't have all of their memory allocated. Technologies like ZSwap and the out-of-memory daemon might be helpful in this area. And this area, memory oversubscription, at least in my experience, in the KVM, for KVM hypervisors, it's mostly avoided. Very, very few people use memory oversubscription, and it's a topic that I think needs more research and more testing in order to provide any form of kind of recommendation of how to do memory oversubscription in Linux. The technologies exist. The validation of these things and kind of recommended config for them is not there. So bottom line on the numbers part, when you have technology that is sufficiently advanced, in our case, for this, the things that help most are just efficiency. How much, I said, maybe it's about 5% for putting all of these other things inside of your compute nodes. And the other part of the sufficiently advanced technology is you need, in order to do something like this, you need these highly available virtual machines which are not managed by CloudStack, because you need to kind of build your cloud management platform, and then that manages the rest of the virtual machines. And the efficiency stack up. So a lot of times when we talk about efficiencies, there are these multiplicative factors that help a lot. We can do this kind of stuff with StorPool KVM CloudStack, and obviously your mileage might vary if you attempt doing a similar thing with a less efficient storage solution like Ceph or something.